Hello everybody. So let's start talking about linear algebra. Okay. Okay. So last time we talked about the linear spaces and give a bunch of examples of linear spaces. Basically, we give for example, and this for example is what we are going to study all the way. The first example is our actual spaces. It is infinitely extended, flat, and with origin chosen. This kind of space. And the second space is so-called R, which is n by 1 matrices over R. Over R, I mean all the entries is real numbers. And the third example is kind of like polynomials, but it is polynomials with bounding grid. And the fourth example is so-called rational functions, which is a polynomial on the top and a polynomial on the bottom. And after that, we said that the way we want to study linear space is by linear combination, and there are infinitely many vectors in a linear space, so we don't want to treat infinitely many guys together. So that's why we want to reduce that, to reduce to the thing that is easier for us to study. So this is the way why we want to use linear combination to study a linear space. And when talking about the linear combination, we are interested in the questions like, if you have two vectors, what are all possible linear combinations of these two vectors? And what are all collections of them? And after that, we define what is the span of the several vectors. The span of several vectors is just a set that consisting of all the possible linear combinations of those vectors. And then, because we don't want to write linear combinations as the sum and not and multiplication, so actually we said that we can use the matrix multiplication to kind of simplify our notation. And this kind of simplification is very useful because the matrix multiplication is associative. You will see in the future that this kind of form is very, very useful. And we can use the associativity of the matrix multiplication to simplify a lot of calculation. So this is the importance of the matrix form of linear combination. And afterwards, we discuss what is linear dependence. Although I haven't defined what is linear dependence, but I give you an example in about two vectors in a plane. When those two vectors can actually span the whole space, and when does not, it is actually depends on whether they are collinear or not. So afterwards, I just conclude four characters for those guys who is collinear, or you can say who is linearly dependent. Just think about these two vectors. Okay, by the way, I updated the notes, and there is something called new note, so which is available if you type in notes in OTTS in my website. And the new notes is a note that I will follow, because the old notes, which I taught last summer, is not. I think it's not organized in a very good way. So it's not in my expected way. So I just make it more clear, and you will see that our class will follow closely on the new note. So if you read something in the class, you can check it online, and then you will see what we taught in class. So notes. Okay, let's continue our topic. As you can see, if you have two vectors, whether they could span the whole linear space depends on whether they are collinear or not. And we are interested in classify what is collinear and what is not collinear. What I mean is not only for two-dimensional space. We just want to generalize this kind of relationship to any kind of dimensions. So we just see there are several properties for the linear dependence, and actually each of those properties are equivalent. So the first property is the same as the second property, is the same as the third property, and it's the same as the fourth property. So they are actually all the same, but they are different point of view. Okay, so the first kind of understanding of what is collinear in this is that we cannot expand the space as much as we want. Because if we had two vectors, we could expect that the space that I want them to expand is two-dimensional space. Because the largest space that two vectors can expand is always a two-dimensional space. But now it is collinear, so the first meaning is exactly what collinear means, which means although there are two vectors, they are only able to give me a one-dimensional space by linear combinations. So this is an intuition about what is collinear. And the first one is actually the same as the second one. Okay, so let's just analyze why it can't give any vectors in a two-dimensional space. It is because of that they together only give us one direction. Because they only give us one direction, so some of the vector, maybe right over here, could be written as a linear combination of others. So like this vector can only be written as a linear combination of this guy, or this vector can be written as a linear combination of that guy. Because of that, so this is the reason that they can't expand the whole space. And the second guy is also, yeah, I mean they are equivalent. So from one of them you can actually deduce the other one of them. Or you can look at three vectors. Those three vectors are co-planar. Okay, because okay, let us switch this case to this case. This case is two vectors. This case is three vectors. These three vectors cannot give us a three-dimensional space because they are restricted on the blackboard. If they want to give us three-dimensional space, one of them must be break out of the board and then like this. But they are all restricted in the blackboard. And the second one is that some of them can be written as a linear combination of others. Yes, of course, because the three vectors is restricted here, and maybe only two of them are enough to expand the whole space. So the third one can be written as a linear combination of other two. Like you can just do it like this, right? And you can see this vector can be written as a linear combination, and going this way and going that way. So these are two examples. This guy, I expected two vectors to give us two-dimensional space. This guy, I expected three vectors to give us three-dimensional space, but they are not. Okay, so the first one, the second one. So what is the third one? The third one is that they must have some non-trivial linear relations. Which I mean is that because they have the linear, because one of the vector can be written as a linear expression, so you can just move one term of the equation to another side, and you will end up with an equation equal to zero vector. And in that equation, all the coefficient is not zero, and this is so-called non-trivial linear relations. So the two, the third one and the second one are actually the same. As like in this case, if this vector is a double of the first vector, let's call it as vector 1 and vector 2. Maybe put a small arrow on that. And the non-trivial relation is just written by the vector 1 plus the vector 2, maybe multiplied by minus 2 is equal to 0 vector. And in this case, you can also find the linear relation, which is for vector 1, vector 2, vector 3. And I don't want to write it because you can finally give an expression of that. And the last guy is that although they can't represent every vector in my that I expected in the space, but actually if I look at the span of them, if I look at the vectors who is able to represent as a linear combination of those guys, but what happened is that the way to represent a vector by them is not unique. So like in this picture, let's say I just want to represent this vector, which is 3, which is the second vector times 3. I call it as W, and then this W is equal to, okay, I can write it as the first vector multiplied by 0 plus, okay, the second vector multiplied by 3, right? But the way to do that is not unique, simply because of this relation. Because I can just simply add these two equations together, and then 0 vector add on any vector is that vector itself. So I can also write this, like W is equal to maybe the first vector times 1 plus the second vector times 2. So which means that this vector, you have a lot kinds of linear combinations that can produce this vector. You can produce this vector by 3 times the second vector. You can also produce that by the sum of those two vectors. There are multiple ways. And this is actually reflected on this equation because 0 vector can actually be produced by some non-trivial linear relations. That is exactly why those vectors have lots of linear combinations. So there are actually four characters of what is so-called 2-vector collinear and 3-vector coplanar, and each of those are equivalent. Any question? This is what we taught last night.
2 and 3, they're the same, right?
Yeah, they're the same actually.
2 and 3.
Yeah.
I understand that all of them are same with 3, but just one of these 2 and 3 are not even the same different, I guess, aspect. Right? It's literally saying the same thing.
I mean, logically they are equivalent.
Right.
But each of the statement is another point of view. It is a different point of view. So the second one, you specify a vector. You make some vector special and say that this vector can be represented by others.
Right.
But for the third one, all of that are symmetric. All the positions of all of the vectors are symmetric, and you see this bunch of vectors have the properties that they can represent the 0 vector by non-trivial linear relations.
Yes.
Yeah. So this is a different point of view, but they are the same. Question? Okay, so as you can see, I conclude so many properties, but now I just want to use one of them to define what is so-called linearly dependence. As you can see, the best one, which one do you want to choose to define what is linear dependence? The third one. The third one, because the third one does not make any of them special. It just says that this bunch of vectors satisfies the relation such that the 0 vector can be expressed by non-trivial relations. So let's define what is linearly dependence. So definition. Okay, so the vector, the bunch of vector. Let's call it V1, V2 until Vn is linearly dependent if there exists non-trivial linear relation among them. So maybe there exists some numbers, there exists some coefficients. Some coefficients. Let's say A1 to AN in which sum of AI not equal to 0. So they are not equal to 0 all the way. So sum of them is not equal to 0 such that 0 can be produced by them. Such that you can write a 0 vector in this way. V1 plus V2 A2 plus Vn An. Okay, I write scalar on the right because it is a right linear space, which means scalar comes on the right. And you can also represent this into a matrix form, which is V1, V2, V3 until Vn, like A1, A2, An. So you can say that A1 until An not equal to 0, 0, which simply means that not all of them equal to 0. So some of them is not 0. So this is a definition of the linearly dependent. So a bunch of vector, which is a real matrix of several vectors. So they are in the same space, and this bunch of vector is called linearly dependent. If there exists some non-trivial linear relations among them. So they are basically what is the definition, and the following word is explanation of what is linear relation, what is so-called non-trivial linear relations. And this is two different kind of representations. So the first guy is just simply you multiply each guy by scalar and sum up them. And the second guy is to use a matrix form, to use matrix multiplication to denote the linear combinations. Any question?
That's a 0 all the way, right?
Yeah, this guy is not equal to 0 all the way, which means that some of them is not equal to 0. So let's say this guy could be 1, 0, 0, 0, 0. I mean, if one of them is not 0, then these two guys are not equal. So you only need at least one of them is not equal to 0. Can everyone see the blackboard? Just such that. Okay. Any question? Okay, so this is so-called what is linearly dependent. Okay, and let's just use this new word. I want to keep this, guys, but okay, let's just use some. Can I erase this part?
Yeah.
Okay.
I have a question. So for A, at least one A is not equal to 0.
Yeah, at least one is not equal to 0. Like you can let n minus 1 of them to be 0. But if you have 1 not equal to 0, then it is non-trivial linear relation. Right. So let's see, okay, example. If I have a bunch of vectors, but some of them is 0 vectors, are they linearly dependent or independent?
Yes.
Why they are linearly dependent?
Because you can always combine 0 vector with another vector.
Yeah, you can always multiply 0 vector by anything, and they are equal to 0. So, so if bunch of vector consists of a 0 vector, they always linearly dependent. Okay, so basically by the definition is that you want to produce a linear relation, a non-trivial linear relations. Because you have 0 vectors, so you can simply multiply 0 vector by anything you want, and it is still 0. Like you can just do this like 0 vector multiplied by 1 plus whatever v2 multiplied by 0 and whatever v3 multiplied by 0. It is a zero vector, right? And it is a non-trivial linear relation. It is because not all of the coefficients equal to 0. Because at least we have 1 over here. So it is a non-trivial linear relation. Oh, sorry.
What about vectors consist of all 0 vectors?
If you have a bunch of vectors, say 1,000 of vectors, but if 0 vectors is in there, then they are just linearly dependent, no matter what.
All 0 vectors.
Huh?
All 0 vectors.
So you mean all the vectors are 0 vectors?
Then it is dependent.
Yeah, this is even more dependent, right? Okay. So what is the intuition? Although I use the definition, say that it is linearly dependent. So don't remember originally why do we want to define linearly dependent. What I mean by linearly dependent is that they can't expand the space. They can't expand the space as large as we want. Because we have like 3 vectors right over here. But the 0 vector only takes a position, but do nothing. So although these 2 vectors might be already give me a plane, right? But here it comes 0 vector. 0 vector takes a position, so now I expect them to give us a 3-dimensional space. But actually, this guy is doing nothing. So it only takes a position, but do nothing. So that's why it makes those bunch of vectors to be linearly dependent, because of this bad guy, right? So this is a linearly dependence. If you have 0 vectors, they are linearly dependent. And you can also think by another kind of perspective that there should be some vector that can be represented as linear combination of others. This vector is a 0 vectors because it is a bad guy, so the most special guy must be green, right? So 0 vectors could be represented as a linear combination of v1 and v2, like v2 multiplied by 0 plus v3 multiplied by 0. And you can think whatever you want that understand why this kind of vectors are linearly dependent. Any question? Okay, so let's just look at other examples. Let's see, can I erase this part?
Yeah.
So let's restrict myself in this one blackboard. Maybe, let's look at something special. Okay, let's look at something general. Let's look at something easier, right? So I just give you several vectors: 1, 0, 0, 0, 1, 0, and maybe 2, 3, 0. Are they linearly dependent or not?
They are.
They are, right? Why? Why is that? Because as you can see, it seems like some guy is redundant. Okay, so you get 1, 0, 0, 0, 1, 0, and 2, 3, 0. It seems like that this 2, 3, 0, it seems like all the entry in the bottom are 0, right? So if you want to produce all the linear combination of them, they will give you at most those guys who has 0 in the last entry. So they can't give us anything in R3. So it seems that they are not able to expand the whole space as I want, because there are 3 vectors and this guy have maybe 3 dimensions. So I kind of expecting them to give me 3-dimensional space, but they are not. Why is that? Because something seems to be redundant, right? And then by the definition, you want to write a non-trivial linear combination of them. You want to write a non-trivial linear relation of them. So how can you write that? What is can you give me the coefficients such that make them to be 0? 2, 3. 0?
1.
Yeah, minus 1. So this guy multiplied by 2, this guy multiplied by 3, plus this guy multiplied by minus 1. Give me 0, 0, 0. Okay, maybe some of you guys cannot see those coefficients at the first look. But another way to produce this coefficient is like, you can always produce the equation like something can be written as a linear combination of others. So like here, you just say that 2, 3, 0, 2, 3, 0 could be written as 1, 0, 0 multiplied by 2 plus 0, 1, 0 multiplied by 3. Like this, right? Like this. And if you have this equation, you just put this guy to another side. So you get 0, 0, 0 is equal to 1, 0, 0 multiplied by 2 plus 0, 1, 0 multiplied by 3 plus 2, 3, 0 multiplied by minus 1. This is the way how you give out such a such an equation. Okay, let's see more examples about linearly dependent. So, can I? Everybody's done. Okay. Okay, and let's look at polynomials. Maybe I will write a bunch of polynomials. Maybe let's say because I want maybe write linear space, so that's force me to write coefficient on the right. But anyway, let's say 1 is a polynomial which is a constant, t squared which is a polynomial, and let's say t plus 1 squared, and let's say t minus 1 squared. This seems to be a little bit harder. Are they linearly dependent or not? They are. Okay, so it might not have an intuition about why is that or maybe what happened. But actually, you can look at the coefficient. So if you plus this guy, so the way you want to see why they are linearly dependent, you have a bunch of, you have a lot of point of view. So the first point of view is that we are expecting them to give us a 4-dimensional space, but they all lies in a this space, like ax squared plus bx plus c, where a, b, c are in real numbers, right? So basically, the dimension is the word that describes how many independent informations you need to describe all the guy in the set. Means how many numbers are there. So you have a kind of intuition that it seems that we only need 3 numbers. We only need 3 real numbers to describe all the guys in this set. And you can kind of see that it's pretty like a 3-dimensional space, just like what we live. And you have 4 vectors right over here. And it seems that they should be expand a 4-dimensional space, but they are all restricted in a 3-dimensional space. So this is why they are linearly dependent. But it is not a rigorous proof. So what I want you guys to do is to use this definition to actually find what is the coefficient of them, to combine everything equal to 0. Okay, maybe the first way we want to do is to find the coefficient. How to find the coefficient? Okay, but let's expand all the thing, right? So let's say t plus 1 squared is equal to t squared plus 2t plus 1, and t minus 1 squared is equal to t squared minus 2t plus 1. And if you add them together, you will get, okay, you have t plus 1 squared plus t minus 1 squared is equal to 2t squared plus 2. Okay, and it seems like that. It's equal to t squared multiplied by 2 plus 1 multiplied by 2, right? And you just look at all these vectors appear here, right? So you just put everything into one side. So what you know is that t plus 1 squared plus t minus 1 squared plus t squared multiplied by minus 2 and plus 1 multiplied by minus 2 is equal to 0 polynomial. So yeah, actually kind of see the coefficient are 1, 1, minus 2, minus 2. And because you have, this is a non-trivial linear relation, so that's why they are linearly dependent, right? I put coefficient on the right because I want to treat it as a rectilinear space. Anyway. Okay, so this is basically this example. This example might be a little bit hard because you don't have intuition. You don't have so much intuition, but this is a rigorous way to treat the abstract linear space. Maybe in the future you will encounter a lot of abstract linear space, which is always have element, which is kind of given in abstract way, and the way you show that they are linearly dependent is to find some coefficient by some algebraic tricks like this. How many dimensions are in the left side? Actually, it's 3. We will see that later. We will define this dimension, and we will say they are 3-dimensional. But up to now, you don't have to know because at first I only explained why you have intuition that they are linearly dependent, and then how to show that rigorously.
Where's the dx term?
Huh?
You know how is this x?
Oh, sorry, it's t. Sorry, this is t. Okay.
Okay, where's the bt term?
Huh? At squared plus bt plus c. Huh?
Yeah, because it's t plus 1 squared. When you expand that, you get
Yeah, you expand this.
terms.
Do you know this?
Oh,
So
yeah,
you
yeah.
get t plus 1,
Yeah.
t plus 1, and then you expand everything.
Yeah.
So you expand this first is t multiplied t plus 1 plus 1 multiplied t plus 1. And expand this again. So it's t squared plus t, expand this is t plus 1. And you combine these two terms. Question?
So is this 3-dimensional because we need dimension to describe the square terms, the variable t terms, and then the...
Yeah, actually, the intuition is that you need 3 numbers to describe all the points.
Okay.
Yeah, so, but this is not the rigorous way to say that.
Yeah.
Afterwards, we will see why. Okay. So this is a linear dependence. Remember the first goal that we want to study linear combination is that we want to reduce every guy into the easiest things, which is that I want to represent everything into a linear combination of those guys. But the linear dependence is saying that some guy is redundant, which means there are some guy which I actually don't need it to give me all the things in the space. So if I want to find the most efficient way, I must take them off, and then I just leave the guy which is efficient, which is enough for me to expand the space I want. So this kind of thing is so-called the linearly independent. So the linearly independent guy is that all the seconds you reverse them. So the linearly independent means that they are in the most efficient way, and they can give us what we expected. So let's talk about the linearly independence. So the linearly independence in this graph means that you have 2 vectors which is not collinear, so that they can actually use these 2 vectors, or say use these 2 directions to reach every point in the space. So linearly independence just simply means that they are in some efficient way to represent each vectors. Okay, but they are not necessary to expand the whole space. So let's see each of the conditions, and let's understand what is linearly independence. And you can imagine 2 vectors which is not collinear in your mind. Okay, the first guy is that they can expand the space as much as we want. So which means if I have n vectors which is linearly independent, I'm expecting them to give us an n-dimensional space. So this is the first guy is that they are. Can you use this? linearly independence. So the first thing that I want that is that okay, suppose that I have a bunch of vectors, say v1, v2, maybe vm. Okay, the first thing I want them to be is that they are able to give me so-called m-dimensional space. I just use the mark because I didn't define what is dimension, but you kind of understand what is one-dimensional, two-dimensional, and three-dimensional space. Which means if you have three vectors, I kind of expect these three vectors to give us three-dimensional space. And the linearly independent just means they are, right? And this is the first guy to describe what is two vectors is not collinear, and to describe what is three vectors are not coplanar. Okay, and how about another point of view? We can use this full point of view of linearly dependence to think about the point of view of linearly independence. Okay, the second guy must be any of them cannot be written by any of them cannot be written by linear combination of others. Saying if you have two vectors which is not collinear, which is that they are in the most general position like this, then any one of them, of course, cannot be written as a linear combination of the other guy. Because that if you want to write this V2, say, as a linear combination of V1, then you will meet some trouble because all the linear combination of V1 is restricted on this line, which is in the same direction of V1. But the V2 is some vector that break out of the line. V2 is some vector that is not in this line because they are not collinear. So V2 is right over here. You can't write V2 as a linear combination of V1. So this is another point of view. What is collinear or what is not collinear? So what is linearly independent? Is the second one. Okay, let's mimic the third one. So they say that there are non-trivial linear relations. So for the linearly independent vector, it must be the only linear relation of those vectors. Are trivial relation. So which means that if you want to combine, if you want to use these two vectors to represent the zero vectors, the only way to do that is that V1 multiplied by 0 plus V2 multiplied by 0 is zero vector. And this is the only way to represent the zero vectors. What I mean is that if you want to modify the number such that they are not equal to 0, 0, then they always represent some other vector which is not a zero vector. The zero vector can only be represented by this way. So they are kind of saying some uniqueness, right? Okay, so what is the last condition? What is the last perspective of the linearly independence? Can anyone guess?
There is a unique way to represent.
Yeah, because I erased that. So, okay, so for any vector, W in the span of that, which is means if W can be written as a linear combination of V1 to Vm, then way to write W into a linear combination of V1 to Vn is unique. Okay, this is so-called the linearly independence. So basically speaking, the linearly independence is that if you have maybe two vectors, the linearly independence of these two vectors will tell you that this two vector is able to give you a plan. It's able to give you every point on the plan by linear combination. And if you have three vectors, then linearly independence of these three vectors means that they are able to give you every point in a three-dimensional space by linear combination. And all of the second one, the third one, the fourth one is that there is some uniqueness. So the third one and the fourth one means that the way to combine them is unique. So the way to write any vector into a linear combination of those guys is unique. And the second one is that the second one tells you that they are the most efficient, which means that if you taken any vector off, then the whole space will collapse. So which means that if you have three vectors that have already expanded the three-dimensional space, right? But if you want to get rid of any one of them, if you get rid of any one of them, it seems that whole space will collapse because like this vector, if this vector does not exist, then the span of those two vectors is not able to give you the other directions. So the linearly independence of those vectors simply means that each of the vector is responsible for a direction. Each of the vector is responsible to give you a direction, and getting rid of any one of them will make yourself lose a direction. So this is what linearly independence. So how do we define question?
What does four-dimensional space look like?
Four-dimensional space. I can draw that on Blackboard, but maybe you cannot imagine. But you just add one direction, but
yeah.
you are actually living in a three-dimensional space, right?
Yeah.
If you ignore the time. The four-dimensional space, you can just think that there's.
But where is it? Where is the
You can think the time as as an additional dimension. So like the three-dimensional space, there's also another way to understand what is three-dimensional space, right? So like if you have a book, if you have a bunch of papers like gives you a book, right? It is three-dimensional, but you can also do something like this. You can put a picture in each of the paper, and then do something like this. Then you will have animation, right? You will have some animation and something is moving, and you can think this direction as time. So you can also think three-dimensional space as a moving pictures, which have the time as another direction. So you can understand four-dimensional space as a space together with a time, and something is moving. At another direction. So
It's pretty hard to imagine.
it's pretty hard, yeah, because you just live in three-dimensional
It's
space.
like time, is it a time
Yeah.
machine?
Yeah, but in the four-dimensional space which we live in today, which I mean is that if you consider time as another dimension, the other dimension is not like the dimension in space, because as you can see, the dimension is at 1 second, right? 1 second. How long is 1 second? It is meters, but multiplied by 10⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻ So they're imaginary numbers. So they are not.
Explain that. What? What?
1 second is equal to this much of meters.
Something like
Imaginary.
Yeah, imaginary.
Yeah, that's complex. Okay.
Yeah, so there are something strange. What that means that you can't go back in time. if we don't have this root of minus 1, then you can. You have that.
So what if you
Why do we have
multiply
that?
by negative?
Yeah, because there are some distance formula which is defined by Einstein. Okay, we are not talking about physics. Yeah, maybe if you are interested, you maybe can introduce the time and introduce the time machine if we can go to the linear form. Okay. So yeah, as you can see, it's pretty hard to imagine four-dimensional space. So let's say where we are. Okay, we are what do we talking about?
The fourth.
Oh, the first one, right? Okay. Yeah, actually, in four-dimensional space, two planes can intersect in a single point. They are not necessary to intersect in a line. Two planes can intersect only in a single point. And in four-dimensional space, you don't have trouble with like computer lines because this kind of thing, like something twisted together, only happens in three-dimensional space. In four-dimensional space, you don't have this knot. You don't have knot theory. And if you knot your lace in four-dimensional space, it will release.
Why?
Yeah, because as you can see, if you have something in a four-dimensional space, right? Okay, I cannot. This is what is three-dimensional space. Now they are linked to each other. They cannot separate. Yeah. But in four-dimensional space, you get another dimension, right? So you can simply move this part to the past, which is like this part, and together with this what is so-called quantum or something, which is in the past, and then you can move this out and move the past guy to now, and then there's no knot in four-dimensional space. So if you can imagine four-dimensional space, you will see very interesting stuff. Okay, we are now talking about topology. Let's go back. Okay, we are talking about linear algebra. Let's restrict ourselves in the linear algebra dimension, right? So, any question? Any question? Okay, so this linearly independence. Which kind of property do you want to use to define what is linearly independence?
2.
2? Okay. Any of them cannot be written as linear. You can define that way, but actually it makes something special, right?
3? 4?
Well, let's use 3, right? Because we use 3 to define what is linearly dependence. So let's use 3 to define what is linearly independence. Okay. Oh, now I can reuse that because I just want to make analog with this to that, and you can see everything. Okay. Oh, I think that I can reuse this already. Okay. The definition is that so a bunch of vectors which I written as a row matrix of vectors v1, v2 until vn. Yeah, they are all less in a right linear space. It is called linearly independence. If independent, if the only linear relation among them is trivial relation. Which I mean is that if you have expressions like this, 0 vector is equal to v1 multiplied by a1 plus v2 multiplied by a2 plus whatever plus vn multiplied by em, it will forces those am to be 0. Forces means that the only way to combine out zero vectors is trivial relation. And basically, you can understand the linear independent by those four kind of perspectives. Okay, so it tells you some uniqueness about combined vector, right? So actually, there are propositions that make this statement rigorously, and it's all on the new version of notes. Although I can write everything here, but yeah, I will write. Okay, let's give you some example about what is linearly independence. So the way to check whether something is linearly independent is always firstly written all of that in the equation, and then use other informations to check whether this coefficient are all forced to be zero or not. Let's look at some examples. So the geometric example is what we already understand, because I just when I'm talking about those properties, I just let you guys to imagine the geometric example. So let's now look at the matrix example. So which is in, let's consider R3. If I give you three elements in R3, like 1, 0, 0, 0, 1, 0, and 0, 0, 1, are they linearly independent? Why is that?
Zeros only solution.
Yeah, there is only solution. So the way to rigorously show that is to write this equation first. So what is zero vector in this R3? Alright, let's leave geometry. Yeah, it's 0, 0, 0, right? Only the zero vector in R3 is 0, 0, 0. And now you are assuming some coefficient such that this 0, 0, 0 could be written as a linear combination of those three guys by the coefficient. So you write as A1 plus 0, 1, 0, A2 plus 0, 0, 1, A3, right? Okay, and up to now you still can't see why those coefficients have to be 0. But you can calculate anyway, right? If you written as the linear combinations, just calculate by what it originally means. So you calculate that is equal to, okay, you multiply everything inside of that is A1, 0, 0, plus 0, A2, 0, plus 0, 0, A3, right? Okay, so kind of interpret what is scalar multiplication, right? And then you know what is addition in this space is just add each of these guys. It's A1, A2, A3, right? So finally you got that 0, 0, 0 is equal to A1, A2, A3, where all these coefficients are just the coefficient that you assume to linear combine to produce this 0, 0, 0. So finally what you have is that 0, 0, 0 is equal to A1, A2, A3. But in order for two matrices to be equal to each other, the only case is that each element are equal to each other. So in this, you know that A1 is equal to 0, A2 is equal to 0, and A3 is equal to 0. So this is what I mean by it forces the coefficient to be 0. So all this guy equal to 0 because they dare to make such a linear combination to produce 0, 0, 0, and they died, right? So this is linearly independent, and we always show several guys linearly independent by this method. So to assume some linear combination such that we produce linear, what I mean is to assume some linear relations, and then you see that we are all forced to be 0. Okay, so this is linearly independence, and we actually need more work to show linearly independence, because because you show the linearly dependence by putting some numbers in that, like some calculation, but you show the linearly independence by proof. So this is maybe the small proof that we need to show whether they are linearly independent or not. Okay, so this is this example. Any question? Okay, I think it's pretty clear. So another example, because I tell that another example is okay. Can I erase this? Let's think about polynomials. I give you a space like what I taught last time, that Px2, which is defined to be all the polynomials was like ax squared plus bx plus c, where a, b, c are all in real numbers. Okay, and now I give you 3 elements in this set. So this set is actually a linear space, and I give you 3 elements, which is x squared, x, and y. Are they linearly independent? Yes. Oh, why? Okay, why is that? Maybe some intuition tells you that they are kind of able to give everything else. They are kind of linearly independent, but how to show that?
Set it to 0.
Yeah, set that equal to 0. So the first way you do is to, okay, I write this quickly in the right, but okay. Suppose that you have ax squared plus bx plus c is equal to, what is 0 vector in this space? 0 polynomial. 0 polynomial means that a function that any value equal to 0. So this is called 0 polynomial. So it is an equation of functions, right? So you can't say directly that ABC is equal to 0 because you don't know why. And then it is an equation of functions. And how do we study function? Is by plugging values. So in order to show that ABC, it forces ABC to 0, we need some algebraic trick to do that, right? So by plugging values, we can actually transfer the equation of abstract functions into the equation of numbers. What is the value that you want to try to plug in? Give me a number. Just give me a number. 2. 2? Okay. If you plug in 2, you will know 4a plus 2b plus c equals 0. Okay, this is not sufficient information for us to conclude that all the value equals to 0. Another value you want to try? 0. 0? Okay, 0 is a clever try because if you plug in 0, you will make this x goes away, right? Okay, let's see. This is by plugging 2. Let's plug in x equals 0. So what we get is, okay, so it's 0a plus 0b plus c is equal to 0. Okay, this equation already forces c to be 0. What any other value you want to plug in? 1. 1? Okay, let's just plug in 1. I suggest to plug in -2. Okay, but let's do 1. So if you plug in 1, you get a plus b plus c equals 0, right? But you already know c is 0 from this equation, so you know that 4a plus 2b is 0, and a plus b is 0, right? Okay, you can solve the equations like, you can do this kind of thing in tons of ways, right? You can write the first equation minus the -2 times the second equation. So what you get is that then 4a plus 2b minus 2 times this equation, you will get 2a plus 0b, right? So you get 2a is equal to 0, which is forces a to be 0. Okay, a is 0, c is 0, a plus b plus c is 0, which is forces b to be 0. So this is the way you try to see whether a, b, c are always equal to 0. Actually, you can also do this by another way, right? You know that 4a plus 2b is just a comment. You know that 4a plus 2b is 0, a plus b is 0. We put everything into matrix, right? This means 4 on the left, 2 on the left, right? So 4a plus 2b is equal to 0, right? And then 1a plus 1b is equal to 0. And then we put that into matrix, right? We put a matrix here. So this guy is equal to 0, 0, right? And there are some common factor on the right. So you just put it out. So you get 4, 2, 1, 1, AB equal to 0, 0. Now get the matrix, right? So what is the inverse of this matrix? You can compute it by the algebraic, right? So the determinant of that is 2. And the algebraic of that is by switching those elements and put minus on those two elements. The algebraic is like 1 minus 2 minus 1, 4, right? And divided by 2. So the inverse is everything divided by 2. 1/2. Okay, this guy is 2. Okay, you know this. This 4211 times AB is equal to 0, 0, and you multiply the inverse of 4211 on both sides. And this guy, okay, let's say everything. 4211 AB is equal to this guy, okay, 1 out of space. 1/2, 1, maybe 1/2, 2, 0, 0, right? Okay. And this guy, because it's the inverse of that, this will give you an identity matrix, which is just AB and equal to some whatever matrix multiplied by 0, 0. And this guy is AB itself, and AB is equal to whatever multiplied by 0, 0. But whatever multiplied by 0, 0 is 0, 0, right? So it's 0, 0, right? So AB is 0, 0. Actually, they are the same way as what I solving equations, but I just want to demonstrate the method of using of matrix, right? Okay. So this is this example. How do you show? Yeah, this is an example that how do you show some guys are actually linearly independent. Any other question? Okay. Let's also look at this example, but let's look at another polynomials. Let's look at those polynomials like x. Maybe you want to give me three numbers.
0, 0, 2.
I'll give you three different numbers.
0, 1, 7.
0, 1, 7. 0, 1, 7. Okay, now I give you three polynomials. Look at here. It's x times x minus 1, and it's x times x minus 7, and x minus 1, x minus 7. Okay, you have three polynomials like this. Are they linearly independent? Make a guess. You have three polynomials. Are they linearly independent? They are. Okay. What kind of trick do you want to use? Okay, firstly, you want to make 0 as a combination as each of these guys. Okay. X minus 1 multiplied by A plus x minus 7 multiplied by B plus x minus 1, x minus 7 multiplied by C. Okay. Okay, so how do you show it is equal to 0? Twice of the values. Anyone?
Like 1.
Plug 1. Okay. If I plug in 1, right? What happened to those guys? This guy consists of a 0 factor, so it goes away, right? And this guy, okay, it seems not a 0 factor, but 1 times 1 minus 7 is negative 6, right? Negative 6 times b. And this guy is
0.
Yeah, goes away because x minus 1. And you plug in x equal to 1, this makes this to be 0. So that's it. 0 equal to negative 6b. So b is 0. Okay. Yeah, we already got one guy equal to 0. We already killed b, right? So how about a and c?
But it's 0.
Plug in 0, right? Okay. If I plug in 0, this guy goes away. right? Because 0 times anything is 0. This guy, oh, it also goes away because it's x. 0 times anything is 0. This guy is still alive, right? Because 0 minus 7, 0 minus 1 equals 7, right? So it's 0, 0 equal to 7c. Now we kill c, right? C equal to 0. Okay. What is the last thing you want to plug in? 7. Okay, 7. Okay. 7. If you plug in 7, 0 is equal to, okay, seems 7 times 6, 42, right? Equal to a plus this guy makes it goes away, right? Plus 0 plus this guy goes away. So 0 is equal to 42a. Which forces a to be 0. Okay, and all the coefficients are forces to be 0 because you can plug in values to actually test everybody. And then all of them died. So they are. So unfortunately, they are linearly independent. Yeah, this is a way to show that some guy is linearly independent. And those spaces is very important, and we will talk about that in the future. Any question?
Can you predict the dimension infinity?
The dimension of that?
Yeah.
I didn't define, but it is 3. You can just think this is 1 is x squared, and every part is a polynomial.
After you're given the number 0, 1, 7, can you tell it very fast by intuition?
There's no intuition for this kind of space. Anyone want to give an intuition? Yeah. Yeah, actually, if you look at the graph, and if you look at the graph, do you want to see the graph?
Maybe around, but this one give you a constant that you can never give the combination first.
This one give me a constant.
You explain that you will get a constant.
Oh.
You can never give.
Oh yeah. What you mean is another way is to expand all of that guy, and actually write that into a linear combination of 1x squared, and then you have some matrix correcting your coefficient and showing that the matrix is invertible. That's something that we are going to talk in the future. And so, as you can see, this space have 2 bases, and each of the bases is very interesting, and actually they are. And we show that they are linearly independent, and you will see these bases, these 2 kinds of bases will even talk more, will even give us more information about what is so-called the Wendsday matrix, and we will see interesting facts about Wendsday matrix in the future by looking at the linear space of polynomial. So you can actually produce something interesting as linear algebra. So this is a linearly independence. Any other questions? Any questions? Okay, I give you some examples, and I said that I want to write this 4 descriptions into a proposition, and this proposition is important because you will know later. Okay, so let's write that into propositions. Okay. Okay. Independent. So linearly independent. Okay, so let's be the right linear space. Okay, ignore this word. Linear space over F. You can imagine this field as R or C or whatever. Just say this is R. So you have a linear space. I said nothing. I just said you have linear space, and then the following are equivalent. So the first guy is that you have a collection of the elements in this linear space, and those collections are linearly independent. So I use is because I just consider this row matrix of the vectors. So I just talking this one guy, so I use is instead of R. This guy is linearly independent. So this one is equivalent to say, okay, so if my W can be written as a linear combination of that, V1 to Vm multiplied by A1 to Vm. This is a matrix notation of linear combination. It simply means that V1 multiplied by A1 plus until Vm multiplied by Am. If W is equal to that, then the way to represent W, the way to represent W is unique. So what I mean is that if W is equal to V1, Vm, A1, Am, and it's also equal to, and suppose that you have another way to represent that. Equal V1, Vm, and then integral forces A1 equal to B1, A2 equal to B2, and Am equal to Bm. The second interpretation, the third interpretation just corresponds to, okay, so that means that any of the vector cannot be written as linear combination of others. Combination of others. So the last one is that, okay. There's a lot of space. The last one is, that's right here. The last one is, if you want to take any one out of that, so say the span of whatever, suppose here is a vector V I plus 1, there are vectors. This is not equal to the span of V1, Vm+1, Vm+1, and whatever. So which means that if I get rid of any of the vector, then the space collapses. So the span of the last guy, which is obtained by just get rid of one guy, take it away, and this space will become smaller, so it will collapse. Okay, so actually, question?
Maybe I'm reading it wrong, but doesn't 3 contradict 2?
3 contradict to the,
Because you say that
can any of the vector in which is any of the vector is in this V1 and Vm. Any of the vector in this guy cannot return as
combinations
of others. Others with
within the set.
yeah, like V1 cannot be written as a linear combination of V2 to Vm.
Okay. But W can because it is not.
Because I assume that W is in the span of that. I already assume that W is a linear combination of V1 to Vm. So here are L plus 1 vectors, and here are M vectors. I just reinterpret the 4 guys right over there.
This is just for polynomials.
Huh? This is for any vector space.
So we did like 4 for linear independence, and 4 for linear dependence, and 4 for.
We did what? we did linearly dependent, we did linearly independent, and this is a propagation of linearly independent. And this propagation is just redescribe those four properties, four
So
perspective
what's
of
the
the.
difference between linear independence and proposition?
Linearly independence is by this definition, right? And the propagation tells you the rigorous way to reinterpret those sentences. Okay, so the proof is on the notes.
Can you explain
Just take a dimension, take a vector out, and take a
Yeah,
dimension.
if you take any vector out, your space will collapse. So like,
There's no like redundant.
yeah, there's no redundant vector. You understand this? So suppose that you have three-dimensional space like this, right? And you have some basis like this. This basis is like this. This is just a projection to the blackboard. And then suppose this is V1, V2, V3. Okay. Remember this vector is pointing outside, right? So they are linearly independent. Okay. Let's say if I taken out this vector, right? If I get rid of this vector, then originally they can span the three-dimensional space. But get rid of this vector will make the whole space collapse to this plane, right? To this plane. So that's what I mean by taking out it will collapse. And taking out that will collapse to that plane. And get rid of this guy will collapse to this plane. So this is basically the first one is corresponding to 1 because they already expand the largest space that we want. So everybody is responsible for direction. So getting rid of any one of that will make your space collapse. So there's no redundant vectors. So basically the third one, the fourth one tells you there's no redundant vectors. But the one that I want to emphasize is the second one. Is that if you already written a vector into a linear combination of those linearly independent guys, then the method of combining them is unique. Can anyone say why is that? Because
A minus B is 0.
yeah, because that if you have those two kind of method to produce W, right? Then you have two expressions right over here. You have two expressions like V1 until Vn, A1, An is equal to V1 until Vn, V1 to the Bn, right? This guy equal. So the equal just means that if I minus them, it should be 0, right? It could be a 0 vector. And then if you minus them, because they have the same factor on the left, you can just factor out the left factors. And then what's left is A1 minus B1 until Am minus Bm. This guy is equal to the 0 vectors. And because that, if you think the A1 minus B1 and Am minus Bm as some coefficient of combining V1 to Vm to produce 0 vector, the fact that V1 to Vm is linearly independent forces those coefficients equal to 0. So from this information, because they are trying to produce 0 vectors, so it forces all of that guy equal to 0. Zero all the way. So each guy is 0 simply means that AI is equal to BI for each I. What I mean is A1 equal to B1, A2 equal to B2, and they are all the same. So that's why the way to produce that is unique. And actually, why I want to emphasize this, because we can use this to do some algebraic to simplify something. Algebraically, I can say this fact as that linearly independent vectors can cancel from left. So what is can cancel from left? Because that if I have this equation, okay, erase this, right? Can I? Okay. I will show that I have this kind of, if I have this kind of equation that they are linearly independent, finally I can conclude is that B1 AN is equal to B1 Vn, right? So in algebra, it seems like that we can cancel these two guys from left together. But if they are not, if they are dependent, you can't do that. But if they are linearly independent, you can do that. This comes from the uniqueness of the of these linear combinations, right?
What can you cancel?
You can cancel the left factor.
Divide by A.
It's not divide. It just if you have this factor times something is equal to this factor times something, you can now say you cancel this.
Only because they're linearly
Independent. If they are linearly dependent, you will have trouble because, say, if you have this vector, you have that, right? V1, V2, V3, and you know that the zero vector is equal to, okay, of course it's equal to V1, V2, V3, 0, 0, 0, 0. It's also equal to like V1, V2, V3 multiply with 1, 1, minus 1, right? So you know that these two expressions are equal because they are both represent zero vectors. But in this equation, you can't cancel this because, as you can see, if you cancel this, you will end up with some wrong stuff. This is not equal. You can't cancel the factor on the left just because of they are not linearly independent. So if you have linearly independence, you can cancel, or otherwise you cannot do that. This is a algebraic trick to kind of interpret this fact. You can cancel the linearly independent vectors from the left. Okay, so this is the linearly independent vectors. And actually, last time we set the matrix form to represent the linear combination of vectors, right? But suppose you have a bunch of equations, and each of the equation is a linear combination, and you can also use the matrix form to represent that. So what I mean is that, okay, so this is the cancellation rule. I will cancellation. Remember, for linearly independent, you can cancel them. If you can cancel them, you can actually convert the problem into matrix, and then you can solve that. So that's why it's important. Okay, so far I've already talked about this, and then now I can erase that, and then say something else. That last time we said that if we have a linear combination, say like W1 is equal to maybe V1 multiplied by 2 plus V2 multiplied by 5, right? I can write that into matrix like W1 is equal to V1, V2 to 5, right? Okay, and I suppose I have two vectors. W2 is equal to V1 multiplied by 3 plus V2 multiplied by 6. And then you can write W2 is equal to V1, V2 times 3, 6, right? But you still want to put these two equations into just one equations. How do you put that into matrix? As you can see, these two expressions has a common factor on the left, right? If you have a common factor on the left, do you want to put that in rows or in columns? In rows, because in rows you can factor out on the left. In columns you can factor on the right. But they are on the left, so we put all the guys in rows. So W1, W2 is actually put that into rows, so we just write each element one by one. V1, V2, 2, 5, and comma, V1, V2, 3, 6. Okay, and by matrix multiplication, the common left factors can factor out. And you end up with this factor and a matrix of matrix, which is product matrix, 2, 5, 3, 6. So you represent like this form. So you end up with W1, W2 is equal to V1, comma, V2, and 2, 5, 3, 6. Okay, so this is a matrix. So and the first column of the matrix tells you how to do linear combination to give you to produce W1. The second column tells you which coefficient you use to produce W2. Okay, the fact is that it tells you that the cancellation rule is that if V1 to Vn are actually if V1 to Vn are linearly independent, you can cancel it. And here this is also true. Suppose that you can write it by another way, like V1, V2, like some other matrix like A, B, C, D. And suppose you kind of get to know that those two bunch of vectors are the same. And if you know V1 and V2 are linearly independent, you can convert this problem into the matrix problem because you can just simply cancel it. So what I mean is that whenever you have these linearly independent vectors, no matter it is multiplied in the left of column matrices or multiplied in front of a Rayleigh matrix, you can always cancel it to convert it to a matrix problem. So this is an addition to the cancellation rules. This is just a notation and the matrix multiplication stuff, and it's pretty formal. Any questions? Okay, let's see how many. We still have 4 minutes. Okay. Okay, now we stopped. We finished talking about linearly independence and linearly independence. Does everybody understand this important stuff? Understand, right? Because it's very important. Okay. Yeah, just don't ask me what is linearly independence before one day from final, right? But someone did in the last summer. So that's why I use 2 classes to talk about what is linearly independence. Okay, still have some minutes, but I'll just say an idea about all the spaces. Okay, we said a lot about the linearly independence, but what do we want to do? We just want to study the space by reduce everything to a linear combination of something, right? What is the something here? Suppose I want to study our 3-dimensional space, and then I want to have some guy that can linearly represent everything in the space. So I should have enough of them to represent everything into 3-dimensional space. Because if you have no vectors, then I can't do anything, right? If I have 1 vectors, although it is linearly independent, but they are only able to express the line. If I have 2 vectors, that's still not enough because I can only represent the plane. I still need another vector. So if I have 3 vectors, it is enough. It might be enough to represent everything to a 3-dimensional space. So we want enough. We want enough vectors, and we don't want too much, right? So here we want as much as possible, but here we don't want too much because suppose that I have 5 vectors that over here to represent everything to the 3-dimensional space. But actually, maybe 3 of them are just is enough, right? So I don't want too much of them. So enough means that for those vectors, you should span the whole space, like E1 to Dn. You should first span the whole space. We don't want too much, so that means I want the most efficient way to express everything into linear combination. So I want them to be linearly independent. So the basis of linear space simply means several vectors that satisfies those 2 conditions simultaneously. You don't get too much vectors, and you are actually enough. So this is what we call as basis. So basis simply means a bunch of vectors. Firstly, it spans the whole space, and secondly, they are linearly independent. So let's just end up here. And next time, we will talk about the basis, and we will show the dimension, what is dimension, and we will talking about change of basis. 就是你的那个系数传在哪儿？是。
可以左边就可以，就是现在左边还是在右边？现在左边是row。
就你在 matrix 里理解到就是那个 row space 就是 left linear space，column space 是 right linear space。然后这是 example， 然后它之所以要传左边传右边，是因为我之后要学习线性映射和线性变换。我如果先把线性映射写在左边的话，我系数就最好写在右边。现在先不用明白，但就是其实这个表示方法并不用太在意，它只是为了让你的那个计算过程不要混淆。
就是你说它这个当时是它的那个 linear combination， 那是不是说它那个 linear combination 的话是它所有的 vector 的 collecting point？就比如说你有3个 vector， 然后就是2倍的它、1倍的它和3倍的它，然后这个3个相加的话等于 W， 它是不是等于它们3个就
相交
的地方？
不是，因为就是你把那个什么搞混了，就是你把那个什么，你在 linear equation 里我说了2个 interpretation， 那两个是不一样的东西。然后你说那个平面相交的那个不是 linear space。那个就是个平面，那个不是 linear space， 所以 linear space 只有那个 vectors， 没有什么相交的东西，就你只有 segment， 你只有一个有向线段，然后你只能 talking about 就是 linear combination， 你不能 talking about 什么 intersection，no intersection， 没有 intersection。
Just really quick, Professor, I don't know if I'm going to be here tomorrow because I have to travel to Boston tonight. I'll try to make it back, but this is my homework for tomorrow.
Okay.
Can I just hand it in?
Yeah, you can hand it today.
Yeah, okay, perfect. I'll just do it here. But yeah, I'll get the notes from him.
Okay. Okay.
I have one question about this problem. When you showed it to us on the board, I wrote that, but I don't understand why that is necessary. Because you could just leave that out and it would still solve, right? Or maybe I read it wrong.
Yeah, I did write it. I wrote this guy equal to this guy. What is that?
Because we know that.
Because you know that this guy equal to this one.
I feel like even though this is true, it doesn't prove that. Like it doesn't prove that the two are equal.
It's not clear why this guy equal to that guy.
Because.
Because okay. This guy equal to the determinant of this guy. You should write one more step. Like you should write determinant of IABI is equal to determinant T times R. Determinant of the determinant of P is equal to 1.
Okay.
And this guy